Have you ever wondered how machine learning models, especially those tackling classification tasks, precisely quantify how wrong their predictions are? How do they learn to improve their guesses, moving closer to the true answers with each step? The cross-entropy loss function is a fundamental mathematical tool that provides this answer, serving as a cornerstone for training classification models. Its derivation stems directly from the principle of maximum likelihood estimation, which aims to find the model parameters that make the observed data most probable. At its core, maximum likelihood estimation seeks to find the set of parameters for a model that maximizes the probability of observing the actual target values from our training data. In classification, this means maximizing the probability that our model correctly assigns the true class label to each input. For binary classification, we often assume the target variable follows a Bernoulli distribution, while for multi-class problems, it follows a categorical distribution. To make the optimization process more manageable, instead of maximizing the likelihood directly, we maximize its logarithm, known as the log likelihood. This transformation is incredibly useful because it converts products of probabilities into sums of logarithms, simplifying computations and preventing numerical underflow when dealing with very small probabilities. Maximizing the log likelihood is mathematically equivalent to minimizing the negative log likelihood, which is precisely what the cross-entropy loss function does. The derivation begins by considering the likelihood function for our entire dataset, which is the product of the probabilities of observing each individual true label given our model's predictions. We then apply the negative logarithm to this likelihood function. For a single training example in binary classification, if the true label is 1, we want to maximize the probability that our model predicts 1. If the true label is 0, we want to maximize the probability that our model predicts 0. When we take the negative logarithm of these probabilities and sum them across all examples, we arrive at the binary cross-entropy loss. For multi-class classification, this extends naturally where the true label for each example is typically represented by a one-hot encoded vector, allowing the formula to pick out only the log probability corresponding to the correct class. This elegant derivation offers significant computational advantages. Using logarithms helps prevent floating-point underflow that could occur if we multiplied many small probabilities together directly. Furthermore, the logarithmic form often leads to simpler and more stable gradients during optimization, making the training process more efficient. From an information theory perspective, cross-entropy measures the inefficiency of using one probability distribution to approximate another, serving as a proxy for how much additional information is needed to describe the true distribution given the predicted one. It is closely related to the Kullback-Leibler divergence. Ultimately, deriving the cross-entropy loss function reveals its foundational connection to statistical principles and highlights its power in guiding classification models. By minimizing this loss, models are effectively nudged to output probability distributions that closely match the true distributions of the labels, leading to robust and accurate predictions across various classification tasks.